So I was doing some research. My personal journey into neural networks started way back in 2003, 2004 when I was getting my PhD in a different context, and since then I was using neural networks in the sense of searching for exotic particles in a large data set that we had at CERN. All said and done, I kind of lost track of neural networks after I moved into the industry. Fast forward to 2017, 2018, now we have a explosion of ML and AI, especially in the field of computer vision and autopilot, things like that, autonomous vehicles, etc. So in any case, I want to share this presentation. Thanks for the opportunity. I'll try to keep it entertaining and also in the spirit of being not too complicated. I'll make it kind of a general expose into neural networks. Let's see how it goes. All right, so well, human cognition is a very important concept that has been around for over 120 years, right? So the earliest exploration of human cognition, if you go back and look, there were people wondering about how we think, what is our apparatus that allows us to be who we are, goes back over 100 years. Now, if you look at the picture on the left, it is very instructive as an example. My 3-year-old, when I showed her this picture on the left-hand side, I asked her what it is, and she said it's a squiggly worm. Those are all squiggly worms for her. So the reason is that she hasn't learned her digits just yet. I haven't exposed her to 1, 2, 3s. But for us, it's very obvious from the context and from the fact that we have a bunch of 2s written. No matter how they are written, we can recognize them as digits. The ones that are shown in the red blinking boxes are kind of tardy, and you can't even recognize them as 2 in some cases. But our mind still interprets them in the right way and gives us the information that we need to process the world around us. Now, if you look at a few others, for instance, they are nicely written, but they are not exactly identical, right? So the field of human vision, the reason I chose this example is because A, it is instructive, B, such a mundane task as recognizing handwritten digits is very obvious to us, but if you give a computer the task of recognizing the handwritten digits and want to write a program to do that, you will soon discover that it becomes extremely complicated. So the question is, we have been writing programs for over 70, 80 years now. The question is, can we allow the computers to process information the way our brain does? The brain has evolved over 540 million years. And the apparatus of the visual cortex is the one that has evolved to an extent where we can today recognize the world around us and make sense out of it. But the visual apparatus itself, which is the eye, hasn't changed much in all of these years. So what changed? What changed is the fact that our brains got bigger and our recognition of signals that are coming to the brain got better and better over time. So can we do such a thing to a computer is the question. Now, I'll take a small segue here and say that today the answer to that question is yes, we can, and I will go a step further and say that we can not only do that, we can also emulate human level or superior than human level intelligence or cognition in some cases. And a general look at the landscape of machine learning, and machine learning, by the way, is the landscape which explores these possibilities, and it's a sub-branch of artificial intelligence. And the machine learning algorithms and the machine learning area is, broadly divided into two cases, two subclasses. One is called the supervised learning, and the other one is the unsupervised learning. So the supervised learning, for example, includes classification problems, regression problems, etc. And the goal of those problems are to either discretely or continuously identify the function, knowing what the input and output already are. For instance, let's say that we can recognize the handwritten digit 2 or 3 or whatever digits that are handwritten. The question becomes, can we make the computer, can we make a machine recognize these digits at a human level, right? So we already know the answer. The answer is, if I input a handwritten 2, the output should be 2. In other words, the computer should be able to tell me that it recognized a 2 in some way, shape, or form. So we know the question, we know the answer. So what are we trying to find out? We are trying to find out the function that maps the input to the output. That's the classification problem. There are other problems such as association and clustering. So association very simply means that, let's say you are checking out something on Amazon. Then when you're in the checkout and we have a cart, then it shows customers who checked out, this movie also liked or checked out other products, right? So that's called associative learning. There is no person coding these things today. And it has become so ubiquitous that we take it for granted that these things exist. And most of these are driven by machine learning algorithms. In general, we can say that machine learning is used across the board, from market segmentation, vision, natural language processing, even into medical fields, bioinformatics, security and field, including fraud detection and text categorization, to name a few. Now, what I'm going to do next is I'm going to just quickly walk us through, without going through the details, and keep it entertaining and short. And in the spirit of keeping it entertaining, I'm going to kind of slide things through on a, you will see this National Geographic kind of a window pop up and move around as we proceed over 100 years of, our knowledge base that we call as artificial intelligence. And this is not a newly emergent technology. It has been around for a long time, and it has made progress in fits and starts. And now is the golden age, I presume, or in the future will be the golden age for this field. So let's go through some really important, milestones and breakthroughs as we go through the slides. So on the top right corner, you will see the National Geographic window pop up and short time frame where these things happen. So in order to mimic how our brain works, we need to understand what our brain is and how it works. And the earliest foundation was laid by Santiago Cajal, who was awarded the Nobel Prize in Medicine in 1906 for his work in understanding the neurobiology. And he was an amazing artist as well as a doctor, a physiologist. And because of his work, we owe a lot to this gentleman, the gentleman who kind of gave us some insights into how our own brain is structured and functions. So the cornerstone of our neural apparatus is a specialized cell called the neuron. In the last count, people were quoting 100 billion neurons in the brain alone, in the human brain alone, but somehow these numbers got reduced to 86 billion neurons in the last few months. You can see a bunch of papers that popped up where somebody questioned, how do we know that there are about 100 billion neurons? And then they went ahead and did some measurements, and they were close, but not exactly close. So there were a bunch of papers that came out. So these 86 billion neurons are specialized cells capable of information storage and transmission. That's the crux of it. And the transmission of information happens everywhere. It happens to other gland cells. It could happen to your muscles, and it could happen to other nerve cells or neurons. So looking at this picture, right, so you can see that there is a central cell body, which you call as a soma. And then dendrites are these tentacles that are coming out of the head. And these are the filaments that connect this cell, for example, to other surrounding cells. And one of the dendrites is an elongated version of itself, which is called as the axon, which is where the signal actually propagates from this neuron to its neighboring neurons. The real learning and the real understanding and memory and all of these, neural activity happens in the gaps between neurons. That's a critical thing to understand here. The gaps between the neurons is where all the communication occurs, and the neural apparatus communication can be either electrical or chemical. What that means is that in some cases, our bodily functions should not depend on chemical communication, because chemical communication using ions is pretty slow. So we need something to go really fast, and nature has made it available to us in two different forms. One is the electrical signals, and then others are chemical signals. So you have involuntary movement. In other words, when you fall asleep, you're still breathing, your heart is still beating, etc., etc. So all of these critical activities are happening because of the electrical signals that are going from your brain to your muscles and body parts that keep you breathing, for instance. So that's one aspect of it. So anything that we do should be kind of modeled on our apparatus. So I'm trying to motivate us to get to a place where we can see that the neural apparatus and the neural networks bear a very close resemblance. Now, it's not enough to know the apparatus, but how does it really work, right? So on the right, you will see a graph. So you just ignore the graph for the moment and follow with me on how the actual communication occurs in the neurons, right? So the first thing is, let's say a signal is generated by stimulus, and these stimuli are everything from the light reflected off of your retina that goes into your brain, or a touch sensation, or olfactory or auditory, any other information through your senses that is going to your brain are called stimuli. And these stimuli go through the receptor cells and go to the neurons through the central nervous system. And these, for example, let's take a look at the flashing stars there. So let's say that the signal arrived at a neuron. A bunch of these signals arrive and they are collected and summed together. That's what happens inside a neuron. And once that summation is completed, the next thing that happens is very interesting. So there is a small potential difference between the neuron and the surroundings. This is called the threshold or resting voltage. So any signal that is summed up that is below this threshold does not excite the neuron. In other words, it says, been there, done that, I'm not going to get excited about this, right? It doesn't say that, but that's basically what's happening. So those are sub-threshold stimuli that you see in the graph below here. Now, any signal that exceeds the threshold, in other words, anything that's more excitable, excitatory signals that come in and add up to a certain threshold or above, will cause the neuron to kind of, jolt and wake up and say, hey, this is something that you need to take care of. So these are basically the signals that get processed. So what happens next is also very interesting, is that there is a kind of a potential that because of the potential difference, there is a signal that is generated that is called the action potential that traverses through the axon into the neighboring neurons. And this traversal happens only if the summation of the signals that came in is above a certain threshold. And this is an important step to understand how the neuron works. Again, the action potential is very interesting. It is a all or nothing process. What that means is, let's say that you have a gun and you want to fire a gun, for instance. You're making your intention clear by actually pressing the trigger, but once you press the trigger completely, the bullet that comes out is coming out at extremely high speed, And the speed of the bullet and the force with which it comes out has nothing to do with you pressing the trigger, other than the fact that you expressed your intention to fire, right? That's exactly what's happening with the neuron here. All the signals that came in and got summed up are expressing the intention. Those are just the triggers. And the all or nothing signal is like the bullet coming out of the gun. So that's the process by which information gets propagated from inside the neural pathways. Now, in order to model this in real life, there needs to be a certain way of, since we understand how to model it now, at least, we need an input. So these inputs are basically the dendritic signals that are coming into the neuron. And then the signals are of unequal strength and number in general. So that's true of our own brain. Then there is an unknown, which we call as a black box, which is a function that we don't know what it is just yet. All of these signals that are coming in as an input are aggregated. And there should be a way to trigger a decision or an action based on some criteria. And the action should be independent of all the input that is coming in to emulate the all or nothing nature of the neuron. Next is the output itself. Output itself is the signal that's sent to the neighboring neurons if a certain threshold is exceeded. So the previous two slides enabled us to come up with a rough model of how the neuron is and should work. Okay, let's go to 1943, fast forward to 1943. So between 1906 and 1943, not much happened in the field of neuroscience as well as neurophysiology because people were busy fighting the world wars, and there were other things that preoccupied the sciences at that time, including building a bomb, for instance. But after 43, the earliest efforts that were done were by two gentlemen, Warren McCullough and Walter Pitts, who's a neuroscientist and logician, respectively, and they proposed what is called as MCP neuron. So it bears their name. So the basic model is what we saw in a real neuron. So you have a bunch of inputs that are coming in, and these inputs, they assume to be binary, which means it's either a 0 or a 1. And then these get summed up into a function f, right? And then based on some criteria, there is a function g, which we call as an activation function, which either triggers, which either fires or not, depending on what the sum of the signals that came in is, for instance. Now, this model was very successful in explaining several things, including, it could model basic logical operations such as and, or, not, nor, etc. And their paper became extremely famous, and a lot of people took interest in, their work. The limitations of this model was, basically all inputs were equal in weight. When we know in the real neurons, not all inputs are equal. What that means is, let's say I want to go watch a movie today, then my criteria depends on two things. A, whether it's raining outside or not, I don't care, right? So that input is negligible. And do I have the time after work to spend, is my calendar free at some point of time? So that's an input. So all of these inputs will allow me to either A, decide to go and watch a movie or not. So that's what this is happening. So not all inputs are equally weighted in my case, but in the case of the early neuron models, they were all carrying equal weights because they were binary inputs. And then the other limitation was that, when do we make a decision, yes or no? When these signals are added up, should the signal be greater than 20? Should the signal be greater than 30? I'm just picking up an arbitrary number here as to when should the activation happen. So these were the couple of limitations. Now let's take a look at what exactly that means and what could it do. So let's say we have two inputs, x1 and x2, right? So if I choose a threshold of 2, and if I sum up the signals x1 and x2, and I want it to fire, meaning I want it to emulate the AND operation, then I have to set a signal threshold to be equal to 1. Here in this right-hand side, you will see the two inputs, x1 and x2, represented in the two axes. So you can see the inputs 0, 1, 0, 0, 1, 0, and 1, 1, for instance. These are the inputs. Now, I want the output to be activated if and only if both inputs are 1. So this line, the dotted line that you see, is called the decision boundary that separates the not firing from the firing. In other words, if both inputs are 1 and only 1, only then I will take action. So the decision boundary, everything to the top right of the decision boundary is yes, and everything to the bottom left of the decision boundary means no. So it can emulate this, which means it can emulate real decision making that the brain probably does. Just another example, if you want an OR, so in other words, I can shift the decision boundary to be going through 0, 1, 1, 0, for instance. And in this case, it will accommodate if either one of the inputs or both are 1, then the decision boundary is yes. Otherwise, the decision boundary separates the yes and no at that point. So in these two examples, you'll see how we could kind of model some basic operations. How do we model complex operations? This can be done easily by compounding or putting together many of these small units together to make a complex or complex decision. And we have known that for quite some time. And that's how the computer architecture today works. Now, fast forward to 1949 to 1965. There were several attempts that were made to kind of hone and zoom in on the neuron and the MCP neuron. And a couple of people, Canadians especially, came up with an amazing set of postulates. Donald Hebb was one of them. So Donald Hebb's observations were very keen in the sense that he put forth the argument that, let's say that you are young and you don't know how to ride a bike or how to swim, and you learn it once. And let's say once you've learned it, there is no way for you to unlearn it unless you have a brain injury or you have some kind of an ailment that will make you forget driving a bike, for example, riding a bike. In other words, if you get on a bike 20 years later, you can still ride a bike. You learned it only once. So there has to be some way to model this in real, this happens in real neurons. So there has to be some way to model this mathematically model this. That was the observation. And the other thing is that this is captured in a very nice sentence called neurons that fire together, wire together. In other words, certain areas of our brain have already seen these kind of signals before. For example, riding a bike or some processes that we do on a daily basis. They have already seen that, been there and done that many, many times. So it almost like you're adding up the memory of all of these decisions that have been made or processes that have been learned and keeping that learning going as you proceed through your life, right? So that's called synaptic plasticity. And the second observation was what is called as graceful degradation. So the graceful degradation stands for, I'll give you an example. Let's say you went to a bar tonight and you had one too many drinks. So the next day morning you're hungover, but you've killed some of your brain cells, but you're still functional. So that's called graceful degradation. In other words, killing some neurons should not completely get rid of the output. There should be some way to gracefully degrade the performance of the neural network if something should happen to one or more neurons in the network. So we have to somehow...
Yeah, I'm afraid the last hangover. It wasn't graceful.
So, yeah, I hear you. So that was one of the inputs that was needed for, making the neuron or the neural modeling better. So Frank Rosenblatt proposed a bunch of changes that became revolutionary And he also came up with the algorithm with the same name called the perceptron algorithm that was able to take these into effect. And the way he did that was, instead of taking the binary inputs, he took the binary inputs and a weight associated with it. So each binary input had a weight which was non-zero, which was a real number, and therefore modeled the fact that there could be synaptic plasticity. And then the graceful degradation was modeled by the fact that he introduced something called as a bias. So what is a bias? So let's say that you have a predisposition to seeing something, for example, the plus sign. And today, if I told you all textbooks have to change the plus sign to mean minus. So 2 plus 2 will then become 0 because the plus sign means subtraction. So you have to overcome the bias of already having known that plus sign is always, addition, and it doesn't correspond to subtraction. You have to overcome that. So that's the fact that you have to overcome that is actually captured in the term bias. And that also allows you to set the threshold to 0 for the activation function. In other words, you either activate or not activate at, by pushing the threshold to 0 instead of a positive number. So these changes allowed him to come up with an excellent algorithm, perceptron algorithm, which is a recursive algorithm, to be able to separate or come up with decision boundaries to separate or to do binary classification. So an example is shown in the bottom right here. So if you see a single cat and a single dog, you can learn that they may or may not be separate. In other words, we do, but you can make a machine learn. And then as you expose it more and more to different cats and dogs, it is trying to learn by making mistakes. And eventually it finds the decision boundary to separate cats from dogs, for instance. So that's that. Now, between 1945 and 1965 is called the long AI winter. The reason it's called the long AI winter is because there were two gentlemen by name Minsky and Papert, who wrote a paper in 1969 saying that, this Rosenblatt perceptron is all great, but the real world is complex, and we have found some shortcomings of this perceptron, and there is no way to get around it as we know of. And because of their work and enlightening work, there was a lot of criticism for the perceptron, and the research in AI kind of fizzled out for over 20 years. There were some brave souls who were doing research at the time, and the problem that actually they were solving to highlight the fact that perceptron was not good enough was what I'm going to describe just now. Let's say that you have two inputs, let's say x1 and x2. You have to model an exclusive OR. So what is an exclusive OR? Exclusive OR is if either or both of those inputs are identical, then the output is 0. If they are not, then the output is 1. So exclusive OR actually models the parity of bits, for instance. So you can say if the bits are of even or odd parity, because if the bits are all on or bits are all off, then the output is 0. And if there are, then you can count the number of bits that are on, and you will get the parity of the bits. And it is also used in swapping numbers without using a third variable. So you can swap numbers without using a temp variable using exclusive OR. So exclusive OR is kind of one of the fundamental operations of logic, and perceptron could not model exclusive OR. So why could it not model exclusive OR? And the reason becomes very simple. Look at the graph on the right-hand side here. So can I draw a decision boundary, which is a line, a single line, and separate out the green regions from the red regions? I mean, no matter how hard you try, the answer is no. You can't do that. You need at least 2 lines. So basically what you need is a decision boundary that says, hey, I'm going to learn and get rid of everything whose inputs are both zeros. And then I'm going to learn enough to capture the decision boundary up to the point where one of the inputs is 1, and then I'm going to exclude everything, which is where we need the second boundary, that has both inputs equal to 1. So it has to kind of bracket the decision boundary with the decision boundary in this case is 2 lines, not just 1. And that was the limitation that a single perceptron had, that it could not model that. So what's the way around it? The way around it is very simple. And what I'm showing here is another complex decision boundary, which cannot even be modeled by 2 lines. So it's actually a line that's curved. So there are nonlinear decision boundaries. There are multiple decision boundaries in real life situations. And none of these could be modeled using the single perceptron that Rosenblatt put forth. Now, the way around it turns out to be adding one additional layer between the input and output. And this additional layer is hidden in the sense that it doesn't participate directly in the output, but it actually captures a whole bunch of important ideas that is needed to either learn or remember what you've learned, right? So basically, everything here depends on the input, and there are 2 important concepts here. One is the fact that there is hidden layer, and the second is that including the hidden layer will allow us to solve the exclusive OR problem. The third thing that came about with this revolution in around 1970 was that people were looking at feedback mechanisms where they could say that once you have the output, if let's say that the output is, let's say you are training this network with 2 inputs, 1 hidden layer and an output to learn something. How do we learn? We learn by exposing ourselves to, we go to school, we learn by rote, our learning is more natural, but in order to make a network learn, you have to teach it. And the way to teach it is you expose it to multiple examples and let it make the decisions. And then you correct it if the decision is wrong and say, hey, this decision turned out to be wrong, so you need to go back and do something. So that's the feedback mechanism that was put in place to be able to train networks to identify or classify using hidden layers. And this hidden layers was an important step in the evolution of neural networks. Now, let's take a step back. So far with a recap, what we have done is, we have modeled neurons to be able to accepting inputs and weight them and overcome the bias and then put out an output. We also have hidden layer in between to be able to model a function that is nonlinear. And the next thing to know is, with this architecture, can we solve any problem? That's the question that we're trying to answer. So what does that mean? Can we ask this neural network to identify a song, given the lyrics? Let's say that we make it listen to a song, and it should be able to give us the lyrics, album, and artist, for instance. Or can we make it interpret real contextual natural language? For example, I'm speaking in English, it has to naturally translate it into Mandarin Chinese as I speak. Can it drive a car? To what level of autonomy can it drive a car all on its own with the passengers inside? So can it do that? It turns out the answer is yes. There was a very important theorem that was proved by Kolmogorov, which says that, remember what we are trying to accomplish here. A neural network is basically trying to find the function given the input and output, right? So we know the input X and we know the output Y. We are trying to come up with the functional form F that maps the input to the output. So he came about and said, you can have a multivariate function, you can have a complex function that can be expressed as a sum and composition of many small functions, and basically able to solve any problem. Now the question becomes, how do we teach the computer or teach the machine or neural network to say that these are lyrics? What does it even mean to say that we're teaching the neural network to listen? The answer is very simple. So you can break up human auditory or any, anything basically that we either speak, read, or write into mathematical forms, like using sine or cosine waves, for example, and then feed that into the neural network and say, hey, this is what a song is, and it's a composition, and you can teach it. So in other words, you should be able to encode human information into something that it can digest and learn, and it should be able to solve the problem thereafter. That's the whole assumption here. Now, can it approximate any function? So in other words, most of our natural processing in our brain happens naturally because we don't know or don't care about the functions, but our brain is naturally doing it. It is trying to figure out complicated structures. It is trying to figure out complex signals that are coming in from multiple inputs and process them. But in the case of a neural network, can it approximate any function? It turns out to be, the answer is yes. A single hidden layer can approximate any continuous multivariate function to any arbitrary accuracy. And this was a very important milestone called the Cybenko's theorem in 1989. So based on that, what can we do? Our recipe should look like we have inputs that are coming in. We encode our human information in some way, shape, or form and input that into a neural network. And presumably it has one or more hidden layers. Only one layer suffices, but let's say that we have multiple hidden layers where it's trying to learn and discern the input. And then we also know the output because we want it to output what humans think it should be. In other words, if I see a 2, I can say it's a 2. But if I show this number 2, the handwritten digit 2, to a neural network, it should be able to give me the output as 2. So in other words, we know the output. How many input nodes in each layer? All of these things, were researched in great detail in between 1980 and 1990s or late 1990s. So that's what is called the universal approximation theorem. So what that means is that a neural network can solve any problem. Now, universal approximation can be shown in pictures, and I went into some detail and actually took some time to look at some activation functions. And one of the activation functions is called the sigmoid function. So the details are not important, but you can say that the sigmoid function is an activation function that can be used to model any function. And the way we do that is the sigmoid function is a function of two inputs, the weights that are coming into the neural network and the bias. So if I change the weights, it actually broadens or shrinks the activation function, as you see on the top left here. Now, the other thing that I can do is change the bias that's coming in. When I change the bias, what happens to the activation function is it moves to the left or right without actually changing its shape. In other words, it depends where the activation is happening. So that's what the bias does. So when I put them together, what I get is a combination or a step function, combination of two step functions, which will make up a bump, which we call as a bump function. So given a neural network with many inputs, the hidden layers are trying to learn the weights and biases so that it can model a bump. So each hidden neuron is modeling a bump of certain height. So when you put them all together, what happens is, let's say you have an arbitrary function that's shown on the bottom left here. You're stacking up all of these little rectangles to make up this arbitrary function. This is a function of two variables, but if you take it into higher dimensions, you're basically building up columns in higher dimensions and stacking up these columns, adding them or subtracting them to form a fabric or a shape that describes the function. And that's precisely what a neural network is doing to learn. Now, what is exactly learning in this case? The way we model learning is simply that, let's say we have a neural network, you have an input, you have the hidden layers and the output, and let's say I have a sufficient set of training examples. So I first have to train it to identify things that I know to be true or objectively true. What that means is I have 1,000 pictures of cats and I pass each picture of a cat through the neural network and see what comes out. So let's say that I pass the picture of a cat and it recognizes it as a cat in some representation. And then I say, good for you. And then I pass a picture of a second cat, which is kind of jumping around. And then the neural network fails to identify it as a cat. And then I say to the neural network, nope, this is not good enough. So I need to do something. What I do is I provide a feedback from the output back to the input and say, hey, you need to readjust your weights and bias so that the output for this particular picture should also be a cat. And then the third time I input a dog's picture, for instance, then it says, no, this is not a cat. It doesn't say it's a dog, but it says it's not a cat. So it's a binary classifier. So in other words, you can think of this training as a way of moving forward where the network is adjusting its weights and biases for every hidden layer and for all neurons in different hidden layers to basically learn about the input data. So that's the objective of the whole exercise is to define a cost function, which basically says is a quantitative measure of how badly the performance of the network is for a given input. And we need to minimize this cost function. That's the whole goal of the neural network. So that is done using an algorithm called back propagation. So the backpropagation does a basically, it's all based in calculus. So you can take the negative derivative or gradient of a function of the cost function to minimize it. But if you take the negative gradient of the cost function with 200 variables, it slows the heck down. Modern neural networks have 20,000, 30,000, 2 million, 20 million, or even billion, inputs. In such cases, there is no way you can do a complete, gradient to figure out the minimum of the cost function. So the stochastic gradient descent algorithm and many other algorithms that have been put forth are trying to minimize the cost function, cost of making a mistake, if you will, of the neural network to improve the accuracy. So if you look at this picture on the right-hand side, it's a very nice representation of, or a cartoon of what is happening with these kind of algorithms that are making the cost function go down, meaning minimizing it. So the contours are representative of the cost surface. The redder the contour, the higher in elevation it is. And our goal is to proceed from an arbitrary point in the cost surface all the way down to the lowest ravine or the valley where the star is. And you can see that different algorithms are trying to push or descend the gradient, if you will, towards the bottommost point in the valley of the cost surface in different ways. So that's basically what the algorithms are doing. They're trying to minimize the cost function so that the input, the desired output rather, is very close to the actual output of the neural network. And at the very bottom, you see the accuracy. So in various cases, the accuracy gets closer up for different training samples at different times. So let's say that for one of the algorithms, you have to do 20 iterations to get to 80% accuracy. And for other algorithms, you have to do 40 iterations and so on. So in general, these algorithms, what they're doing is they're trying to find the minima, the global or the local minima in the cost surface by traversing the cost surface and reaching a global minimum. So what are the different learning handles we have on these algorithms? The learning rate is one of them. So what learning rate means is that if you look at the surface on the top here again, which is a cost surface, our goal is to find the set of weights and biases which minimizes the cost. So you can start at any random point on this cost surface, and your goal is to tweak or twiddle all the different parameters in the weights and biases of each neuron so that you reach this end goal, which is here. And the way you do it is using training samples, and you mix them up you randomize them and you pass these training samples through your network and let it do its job. And as it's doing its job, you're providing the feedback of whether it did a good job or not, and then it's learning. In many cases, there should be a convergence towards the global minimum, but there is no guarantee that there is a minimum in many cases. So that's the job of many different modeling approaches that are used today in training neural networks. Let's say, for example, there is also this thing called as overfitting. So in other words, let's say you want to separate the reds from the blues here in the bottom picture here. So you want to classify two things as cat or not cat, for instance. All the red dots are not cat and all the blue dots are cat. So the simplest thing for you to do is to draw a line, which may include some red dots, but it is a simple enough line to separate the two classes. But overfitting, you can see the surface that is actually blinking. You can actually make up a surface that separates every red dot from every blue dot, and that becomes overly complicated. In other words, you have trained the neural network so much that it does an excellent job of figuring out which one is a cat and which one is not a cat on your training samples, but it may or may not do well on the real life or the real scenarios where you take it to the wild and say, hey, identify cats and dogs for me. So that's called overtraining. So the simplest thing is Occam's razor, which means that the simplest answer is usually the right answer. So we should be able to model things just right, don't underfit and don't overfit to be able to separate or do classifications. Now into deep learning. So what is deep? As we saw, we have multiple hidden layers in a neural network. Ideally, we need one hidden layer, but modern neural networks have 7, 8, 9, 10, 20 layers deep these days. So an illustration of it is shown on the right-hand side here. This is most recently a paper from 2006 or so. This was the ImageNet classification that used what is called as a deep convolutional neural network, where the classification, the image recognition exceeded the human threshold in this case. So the deep here signifies that there are many layers, hidden layers between the input and output, and each hidden layer is basically doing some specific task of identifying or learning something deep. What does that mean? That means that it can basically hierarchically learn different features. So the first layer could be learning about the edges, the second layer could be learning about the texture, the third layer could be putting those two together and learning about hierarchical features, the fourth layer could be doing some anti-correlations or correlations between the layers that have learned something in the previous layers, and so on. So is that how our mind works? Is that how our brain works? We don't know for sure, but these deep neural networks seem to suggest that that's how our brain actually works. It has several layers deep, of neurons and neural connections that kind of learn different features and different aspects of the problem to recognize things. And every layer that passed forward is actually learning something and passing it forward. And if it doesn't learn anything, it just doesn't dilute the signal, but it just passes it on as is, intact. And at the end, the hope is that any signal that's coming in as input will be able to be classified or learned as the output. So one of the really amazing achievements came about in 2014 when a bunch of AI researchers from Israel and Facebook came together to put together the DeepFace. This is a very complicated network in itself, and it is shown in picture here. So the DeepFace architecture consists of several layers. So you can see the three layers here that are extracting the low-level features like edges and textures from a face. So even before you do that, if the face is turned sideways, you need to be able to, three-dimensionally move this so you have a frontal information and then figure out the features of that face. And then you learn about the low-level features in the first 3 layers. And in the next 3 layers, you basically learn about the different filters. And then you put them all together in the end and correlate them to be able to identify whatever that you're identifying. In this case, it turns out to be face. So if you've gone to Facebook and ever tried to tag your friends, some of the technology behind it is basically deep face. So where are we going from here on out? So 2017 and 2018 have seen remarkable improvements in Tesla, for instance. Tesla is coming out with version 3 or version 2 plus, I think, of the autopilot, which has amazing, deep learning features embedded in it. You have the real-time BERT encoding and decoding that is used by many people, including the United Nations. You have the AlphaZero that came about that can master any game within hours. And then it's not just about the benchmarks and the competitions in the deep learning space that's exciting today. It is the fact that we can reach human level, in some cases surpass human level intelligence, and we can build that into machines. It should be taken with a grain of salt that all of these advancements are not exactly without their drawbacks. You can see some of the literature and you can appreciate how hard the problem that we're trying to solve is because of the fact that, there are so many things that we don't know just yet. In general, I want to close by saying that, this is not that the machines are coming to take over. The machines are here to stay, and hopefully with a better input from us, we'll be able to have machines interface with us and work with us to be able to solve more complicated problems. And I want to close by actually showing you a video, which I think is one of my favorite episodes from Silicon Valley. I don't know if the volume is loud enough, but I'm going to play it. Can you see my screen with the YouTube video?
Yes.
Okay.
What will you say if I told you there's an app on the market?
We're past that part. Just demo it.
Let's start with a hot dog.
Yeah, the internet is not very good in the office. I guess we'll watch it later.
You could just play it on your computer.
Jinyang.
I'm going to I'm going to let you watch it. I'll share the. I'm sure you have seen it. Some of us have seen it, but this is the hot dog or not hot dog episode from Silicon Valley. And Jinyang has built a binary classifier that can classify hot dog or not hot dog from taking pictures of food, and he calls his company Seafood. Anyway, so I'm going to close with that. If there are any questions, I'll take it now.
None here in the meeting
Did I
room.
lose the audience? Okay.
No, it was very dense, but it was very interesting.
Yeah, and
Yeah.
guys, I saw somebody recorded, right? So unfortunately, I was pulled several times during the meeting for another topic. So do we have can somebody upload recording to, I don't know, to whatever, Core or whatever, and share the link?
I'll send that out. This is Raj.
Thank you, Raj. So, well, just send to everybody who been in this call, so it will be. It's actually, I believe, it's a really interesting topic, and I believe it will be important. Well, importance of this will be only rising.
Yeah.
Well, thanks for taking the time, Venkat. That was a lot.
Yeah. It looks like you put in a lot of work into the slides, Venkat. Thank you very much. All right. If there is nothing else, we'll see you in the next session. Thank you all for attending.
Have a good weekend.
Bye-bye.